Chemistry students, we're about to introduce Unit 3, and in this unit we're going to trace the development of the atomic theory. That is how we understand the composition of matter.
And the first objective is to recognize the contributions of Democritus and John Dalton to the development of the atomic theory.
And we're going to summarize the Dalton atomic theory and look at the experimental evidence he had for the theory.
And lastly, state the law of definite proportions as well as the law of multiple proportions, aka Dalton's law.
So the reading section would be the first section of chapter 4, which parallels the lesson we're about to go through. So to really look at the atomic theory, we've got to go back about 2,500 years ago to the Greek Empire. And there were men at that time called philosophers who sat around and thought up big thoughts about stuff. And their whole premise was that the world could be entirely explained through logic and reasoning. However, and this is a key point, the philosophers didn't do any kind of experimentation. They had no evidence that other than logic and reasoning. So if they could reason it, one of their things they philosophized was teeth. They believed since men had larger bodies that there were more teeth in a man's mouth than a woman's. Never once did it occur to any of these brilliant thinkers to actually open a person's mouth and count them. They just assumed because they reasoned it out that it was correct.
All right, so the first person we're going to talk about was a Greek philosopher, Democritus. He was a philosopher who proposed matter was composed of tiny, indivisible particles called atomos.
Atomos, which is the Greek word, I think, for indivisible. And he came up with this elaborate scheme of things where each different kind of matter was composed of a different variety of this atomos, which actually shares a lot of similarities to what we actually now believe about matter. However, what happened, Mr. Hunter?
Well, the other philosophers later rejected this idea in favor of a different concept. So the sad thing was, I think it was Aristotle argued and won the argument and said that atomos wasn't true, and that set us back.
Matter was made of earth, air, fire, and water, and they were all connected, and one could change into the other, and it was kind of a crazy. Now we would consider it crazy, but
then it took place.
That's what people actually chose to believe in the absence of any evidence. That Democritus' ideas were pretty much forgotten about for the next couple thousand years.
All right.
So jumping forward to the early part of the 1800s, there was a British school teacher named John Dalton who was kind of also did some backroom science in his house, and he actually proposed the world's first atomic theory based on evidence, and he actually chose to call it the atomic theory in honor of Democritus, because he had read through Democritus's teachings on this, and he found that there was a lot of truth to it.
And I think he used the knowledge at the time. One of those was the law of definite proportions, and he knew that all the elements in a given compound was always found in the same proportion by mass.
Right. That had been proven experimentally by it was Lavoisier, I believe, in France a few decades earlier. And Dalton was investigating, how the mass ratios of matter and these chemical changes. And he made what was his probably greatest contribution was you could actually get different ratios of mass ratios of the same two elements. So, for example, compound A, he found would take 3 grams of carbon and then would absorb 4 grams of oxygen, and you'd get this compound of carbon and oxygen. But then he also found if you burned the carbon in a larger amount of oxygen, that the same 3 grams of carbon would absorb 8 grams of oxygen. And the key point that he recognized is the number of grams of oxygen in the second compound compared to the first compound were always related by a small whole number. 1 or 2, 3, 4, something that was a whole number ratio. And that was a startling discovery. And he needed to come up with a way to explain that. So that was kind of the start. I started thinking, why is it always a 2-to-1 ratio? Why not a 0.85 to 1? Why not a 1.7 to 1? Why always a whole number? And that's where the atomic theory came from.
All right, let's take the next one. This gave Dalton's law, also known as the law of multiple proportions, and it states that when two or more compounds can be formed from the same elements, if the amount of the first element is held constant in each, and the masses of the second element in the compounds are always related by small whole number multiples.
And so thinking about this, Dalton came up with a very logical explanation, but his logical explanation was based on his experimental evidence that the reason why it's always a perfect whole number ratio is that these elements are actually made of these tiny discrete particles, and that they're combining in a specific way, and that these different compounds had different numbers of particles of the one element in relation to the other one.
All right.
So if you look at that, if the one compound has 2 atoms of the element and the other one has 1 atom of the element, that would exactly explain why that's a perfect 2-to-1 ratio of their masses.
Okay. So here are the 5 postulates that Dalton came up with and is now known as Dalton's atomic theory. And the first one is very important. He said that matter is made of tiny particles called atoms.
So again, he chose the word because of Democritus. The second postulate is that atoms are indivisible.
Yep, and then his third one is the atoms of a given element are identical in mass and other properties to one another.
And its counterpart would be the atoms of different elements are different in their mass and their other properties. And he wasn't exactly sure what these other properties were, but he figured they must have had some other properties.
And then lastly, atoms of different elements can combine to make compounds. In a given compound, the atoms always combine in the same relative numbers. So that would be the law of multiple proportions and definite proportions.
So all of what he was seeing was rolled into this theory, and of course, the theory is an attempt to explain what he was seeing in his law of multiple proportions. And we've revised the atomic theory somewhat, but it largely still holds true.
Yes, it does.
We'll look at the places where the modern atomic theory deviates from Dalton's theory, but the essence of it is still there. And I do want to throw in one more thing. I was doing some reading on this. If you look in 5 different chemistry textbooks, you will see these 5 postulates worded differently, and some books might only have 4 postulates. They kind of roll a couple of the ideas together. I've seen 6 postulates in some of the textbooks, so it's a little foggy on exactly. I haven't looked at Dalton's original work to see, but this is the 5 that's pretty much word for word out of what's shown in our textbook.
Yep.
So along with his theory, then Dalton started to imagine what an atom might look like, and he came up with what we call the solid sphere model of the atom. So he believed that the elements were each made of these little particles that were indestructible, little indivisible solid spheres, kind of like tiny indestructible marbles. And so I have, the black one could be one element, and we'll illustrate his law of multiple proportions. So let's say the first compound, let's say the black one here is carbon, the red one could be oxygen. So in the first compound, the carbon atom combined with a single oxygen atom, and in the second compound, the carbon combined with 2 oxygen atoms. Hence, the weight of oxygen in this compound is exactly double the weight of the oxygen in that compound. Now, he had no idea what held them together.
He thought they were little barbs, to be honest, or Velcro.
He thought it was some kind of like, atomic-sized Velcro or little hooks or something. He wasn't really sure about that. And that came later, and we refined the model of the atom. But in essence, Dalton did have, that's exactly how we still picture compounds going together today.
Alrighty.
So for your post-video questions, we have 3, and the first one, see if you can spot this one. The Greek philosophers were no doubt great thinkers, contributed a lot to world literature, humanity, our understanding of ourselves, but they really can't be considered scientists.
Yep, tell us why. And then how did the discovery of the law of multiple proportions lead to Dalton to propose his atomic theory? And then we give you a nice one that gets you to try the law of multiple proportions out for yourself. So good luck, and we will go over these tomorrow.